everyone. Okay, so welcome to Math 211. This is now, I think, lecture 14. And we are going to finish chapter 12 today, hopefully. I actually subbed for the other Math 211 class today, and they did chapter 13, which means they're either ahead of us or they possibly maybe skipped a chapter that we didn't. I don't know. But either way, we should move. We should definitely catch up to them. So we definitely did this. I remember we did this. So we did the Robin Hood method. We did that. 14?
Yeah.
Page 14. Okay, mean versus median. Okay, so we have two measures of center, the mean and the median. Those are the two big ones. We also have the mode. But the mean and the median are the two big ones. And the question is, when do you use the mean and when do you use the median? Is there a preferred scenario where one is better than the other? So let's take a look at what we have here. We have a distribution that's skewed to the right. You can see that the tail's on the right side. Things are bunched up over here and the tail's on the right side. We have the box plot, which is 25% packed in tight, the next 25% pretty tight, the next 25%, and then the following 25%. So either way we look at it, we got a long tail on the right side. And when that happens, as we've already determined or spoken about, we know the mean is a non-resistant measure. The mean is usually affected by outliers, whereas the median is a resistant measure. The median fights the outliers and skewness. So as you see there, the mean is pulled in the direction of skewness more so than the median. And if it was skewed the other way, of course, it would be in the opposite direction. And of course, if it's a symmetric distribution, then the mean and median should both be in the center. So what we see is that when there's skewness, the mean is pulled more than the median. As a result of that being the case, the median is the better measure to use when there's a significant amount of skewness present. So when there's a lot of skew, use the median. If it's symmetric, the median and median are roughly the same anyways, but in that case, we use the mean because it is better than the median, especially for more deeper theoretical reasons. So here's an example. In news reports, house prices and other strongly skewed distributions are summarized using the median rather than the mean. If you think about house prices, the majority of them are packed in tight around a standard, 1-story or 2-story single family home. And then of course you have the really, really big ones where the prices can get fairly astronomical. So a distribution of house prices might look something like what we have in front of us. We see it's strongly skewed to the right. You got a lot of skewness on the right side. And as a result, we would want to use the median. In fact, the mean is 844,000, whereas the median is 769,000. The mean is pulled more to the median. Okay, it says mark them on the graph. Well, okay, 769,000 would be, let's see, 4, 5, 6, 7, 8, about here. That's the median, whereas the mean would be about here. So this is the mean, and this is mean, and this here is the median. So we see the mean is pulled more to the right than the median, almost $100,000 more. So then it says, what makes the mean larger than the median? Well, it's the skewness to the right that makes the mean larger than the median. It's pulled in that direction. So then it says, estimate the values of the mean and median if the outlier, that big house over there with 2.6 million, hadn't been on sale that day. This is just Northridge, by the way. So these are the houses in Northridge, October 13th, 2017. So there's not like, any like $25 million, Beverly Hills, Bel Air style homes, but you still have a $2.5 million one. So if that hadn't been there, What would have happened to the median? And what would have happened to the mean? What happened? What would happen to the mean and median if that was not there? Anyone?
Well, the mean would still be larger than the median, right?
The mean would still be larger than the median because it's still skewed to the right.
So do you mean like where it would be, where they would be?
Yeah, roughly where, like how far would I move, or would I even move?
To the
The mean
left.
and median, huh?
They would both move to the left.
So I agree with you on the mean, but why would the median move to the left? I mean, I agree that it moves to the left, but how much will it move to the left? Right, the median is the middle data point, right?
Yeah.
If you remove one data point, let's say you have, I mean, what's the frequency here? How many houses are there in total here? A couple hundred?
66.
I'm sorry?
166.
166. So that's right, it says it right there. So the median of 166 houses is halfway between the 83rd and the 84th, right?
Yeah.
And the 83rd and the 84th are pretty close to each other in terms of prices because they're both in this same tube here. If you remove one data point to drop it to 160 to 165, then what's the median now? Which data point?
Would be like 82.
83rd.
Oh, 83.
So it went from halfway between the 83rd and the 84th to the 83rd. So assuming that the 83rd and the 84th are fairly close to each other, the median wouldn't have changed that much, would it?
No.
Not much. Whereas the mean, on the other hand, might drop a pretty large amount from
Because
a
$2 million house is gone, right?
yeah, exactly. From a $2.5 million house being, that has a significant effect on the mean. So I think they would both go left. The median would barely move to the left, whereas the mean might move more so. Does that
But
make sense?
The mean would still have to be larger, right? Or
The mean would still be larger because there's still a skewness. So I would
Okay.
expect the mean to still be larger than the median.
Okay.
That's correct. Okay. So what do you think? What do you think realtors prefer to tell people? Oh, sorry, why do you think realtors prefer to tell people the median rather than the mean price?
because it's a smaller price.
It's a smaller price. Yeah, it's like, I'm thinking of living in Northridge. Oh, okay. Well, the average price in Northridge is this much. Is what was it? It was 845,000 versus 769,000. People want to pay less. They would love to hear the 769 versus the 845. Makes sense, right? Okay. It also illustrates that the mean is sensitive to outliers, while the median is resistant to outliers. The median is a resistant measure. It says that the outlier were not in the data set, the mean would drop about $11,000, while the median would stay exactly the same. This is just the data. You can't get this from the graph because we don't know the exact data points. But whoever made the graph does know the exact data points. They're telling us that the mean would drop about $11,000, while the median would stay exactly the same. Okay, which is ballpark what we expected in the first place. Correct? Yes, no?
Yes.
Okay. So a first grade class made this blank of the number of letters in their first names. What type of graph is it?
A dot plot. Oh no.
Oh yeah, it's a dot plot.
Histogram.
I can see it being a histogram. Well, a histogram is when you usually have continuous data. So you have like 1 to 2 and you include all the numbers in between, and 2 to 3 and all the numbers in between, and so on. I think a dot plot is actually a slightly better term to use here. Because each of those stickers is basically a dot. Would you agree with that?
Yes.
Yeah, histograms are usually better for continuous data because you want to have those classes. The mean is about what? What would you guess for the mean?
In between 5.
Yeah, like 4 or 5.
Well, you think before between 4 and 5, you said?
I'm saying that. I don't know.
I would say maybe around 5.5.
Okay, so let's take a guess how accurate 5.5 is. And let's do it by the Robin Hood approach. To get to 5.5, each of these three have to go a half unit to the left for a total of a 1.5 change, correct? Because 6 to 5.5 is 0.5, 0.5, 0.5 for a total of 1.5. 7 to 5.5 is 1.5, 1.5, 1.5 for a total of 4.5. 8 to 5.5, 2.5, 2.5 for a total of 5. And then 9 to 5.5 is 3.5. So the ones on the right, this adds up to 5, 9, 10, 13, 14.5. The total distance traveled by the ones on the right to get to 5.5 is 14.5. Here we have 0.5, 0.5, 0.5, 0.5, 0.5, 0.5 for a total of 3. 1.5, 1.5, 3, 6, 7.5. This one gives us a total of a 10.5 to the right. So our initial guess was 5.5. But do we want to refine that guess by saying it's a little more than 5.5 or a little less than 5.5?
A little more.
A little more. Of course, I can also do it the good old fashioned way, which is 4 5 times, that's 20, plus 5 6 times, it's 30, plus 6 3 times, it's 18, plus 7 3 times is 21, plus 8 twice is 16, and then a 9. And then divide that by how many stickers do we have? 6, 7, 8, 9, 10, 6, 11, 15, about 20. And I get an actual value of 5.7. So this is the actual. So 5.5 wasn't a horrible guess. Yeah, it told us to move a little to the right, and the math gives me 5.7. So make a frequency table that gives the same information. How many 3s were there?
0,
How many 4s?
5,
How many 5s?
6.
So 0, 5, 6, 3, 3, 2, 1. 0, 5, 6, 3, 3, 2, 1. 0, 5, 6, 3, 3, 2, 1 for a total of 20. Four times 5 is 20. 6 times 5 is 30. 6 times 3 is 18. 7 times 2 is 3 is 21. 8 times 2 is 16. 9 times 1 is 9. This adds up to 114. And then 114 over 20 is 5.7. Notice how I didn't add 5 plus 5 plus 5 plus 5 plus 5 plus 5. I recognize that 5 occurs 6 times, so why not just multiply 5 times 6?
Can that just be another way then to getting the mean?
That's probably the best way of getting the mean
Yeah.
because it's very quick.
Is it very, yeah, it's very quick. Is
Yeah,
that how you
very-
just did it earlier with your calculator?
Yeah, that's what I did in my calculator.
Oh, okay, perfect. Because I was like, what is he doing?
Yeah, that's what I did in the calculator.
Okay.
So in general, we know X bar is the sum of the data points divided by N. But now we see we can do it a different way and say it's a sum of each data point multiplied by how often it occurs. So we actually write it like this, xi fi. So the ith data point times the ith frequency. So the last example, we had 4 times 5 because 4 occurred 5 times, 5 times 6 because 5 occurred 6 times, 7 times 6 times 3, 7 times, I don't even remember what it was, but you multiply each by how often it occurs, you add them together, you divide by n, and that gives you the mean. Okay, so the only difference between the old one and this one, copy your formula. Also compare your formula to the formula for expected value. So I just had it here a second ago. Sum of x times sum of each entry over n, like this, which I can write as a sum of each entry times its frequency over n. But how often it occurs divided by how much, that's just the probability that it occurs. So we see that it's the same formula, at least conceptually, as the formula that we calculated earlier for expected value. Each outcome times its probability, add it all up together. This not only gives you the mean, but it also gives you the expected value, which means the mean is the expected expected value
Every time.
every time. Every time. So the mean is a number of things. The balance point, equal distribution value, and now we see it's also the expected value. By the way, here is the original graph with ones from other teachers. What is good and bad about each type, right? So we have this one down here, and then we have this one, like the one on the left, actually gives each name and how many letters are in each one. What is good about that and bad about that? Or just good, or just bad?
Comparing it to the first one we saw, it's just kind of like flipped, right? Like if we spin it, it'd be the same.
Well, not exactly, because this first one that we saw, which is down here, this one gives us, it tells us that there's 5 kids that have 4 letters in their name. Like, for example, Juan is one of them, right? 4 letters.
Uh-huh.
But if this was longer and it lists all 20 names, it has the same information as this, but this one kind of collates them by frequency, how often they occur, whereas this one does not. This is just the
Yeah, that
actual
just
data
tells
point.
you. Yeah.
Okay, so this is a dot plot or a histogram, if you want to think of it like a histogram, although I think a dot plot is better, is a visual display of the information, which is easier to look at as a whole. But notice how we don't get the actual names like we do here. So we lose some information, but it still gives us some information, makes it easier to see what's going on. This one here, I don't even know what's going on here. What is going on here? Oh, I see. So this one here, Matthew, Addison, Spencer, Patrick, and so on, right? All these names are here. But again, not collating them, not saying, a frequency table for how many 3-letter names, how many 4-letter names, how many 5-letter names, and so on. It just gives us the actual information, but there's no summary. And at the end of the day, we don't, imagine you had to write a report where you took thousands and thousands and thousands of data points, and then you just write them all down and give it to your boss and say, here they are. And he's just flipping, or she's just flipping through this notebook of just numbers. Whereas a summary display gives a much better understanding of the patterns that are going on versus the actual original data points. Hopefully that makes sense. And then finally, the last page today, or at least of this section, chapter 12, is the weighted mean. Now, usually when you calculate an average, like if I say, oh, we took 10 tests, what's your average? You say, okay, I'm going to add up my 10 test scores and I'll divide by 10, and that's my average. But what if some of the tests count more than others? Then we want a weighted average. So for example, in his first semester of college, a student took 15 units, earning a GPA of 3.0. He took 12 units the second semester, earning a 3.5 GPA. What's his GPA at the end of the freshman year? Now you might say, oh, 15 units the first semester. Sorry, 3.0 GPA the first semester, 3.5 GPA the second semester. So on the average, 3.25. Is that good logic? .0 the first semester, 3.5 the second semester. Is that good logic? Yes, no, maybe so. Nobody cares. I want to go home. I hate this class. Give me something.
No, because in the first semester he took 15 and the second one he took 12.
Yeah. So the number of when he took a 15 units, that GPA should be a heavier weight than the other one where he took 12 units. It should count more. So that his GPA should be closer to 3.0 than 3.25 than 3.5. The question is, how do you actually compute it? So it says 14 of 37 students at the University of Massachusetts were able to complete this problem correctly. The other 23 students got it wrong, most of them saying it was 3.25. How do they get that? They just average the two numbers without taking into account that one of them was a heavier weight than the other. So the question is, what is the correct answer? Would anyone like to venture a guess at what the correct answer is? Let me just do it here quickly. Okay, I got it. So what is the correct answer? Who would like to take a guess? And if the answer is I have no idea how to compute it, that's totally fine. But give me something. We'll see if any of us can match those 37 students at the University of Massachusetts that got it correctly. Sorry. Anyone?
If you had the grades for each class, would you be able?
Yes, if I had the grades for each class, I can do it, but I don't have them. I just have this information. Yeah, if I had the grades for each class, it might be a little bit easier, assuming, of course, that each class was weighted equally. But doesn't say that either. I mean, some of them could be 1 unit classes, some of them 2, and so on.
3, yeah.
Anyone?
Professor?
Yes.
I'm sorry, I'm just still a little bit confused about the formula with the eyes. Is that the formula we would be using for this one?
You could, but the I just stands for basically what it means is there's 2 data points here, correct? You have the first semester and the second semester. So I would be either 1 or 2 for the first X, the first frequency, the second X, the second frequency.
Okay, thank you.
Okay, it is not 3.318. Remember, we just established it should be closer to 3.0 than 3.5. So it should be less than 3.25. But Sabina, did I answer your question or are you still confused about that?
No, I understand now. I don't, could we, during this class, would we be able to go over an example, just like plugging things into that equation, or is it not?
Yeah, I mean, we're doing it right now. Let's for this question. It's recognizing how to apply it.
Wait, how did
So
they even get 3.25?
I'm sorry.
How was 3.25?
Oh, well, one semester was a 3.0, one
Oh,
semester was a
divided by 2, yeah,
3.5.
sorry.
So just on the average, right?
Yeah, I was dividing it wrong.
So here's how we do it. We take the first data point, which is 3.0, and we're going to multiply it by something, which we'll get to in a minute. This is my x1, my first data point. That's my x1. And then we're going to add it to my second data point, which is 3.5. And we're going to multiply that by something, which we'll get to in a second. And this here is my second data point, x2. First data point, second data point. This one here is essentially how often that first data point occurs, its frequency. And this point here is how often the second data point occurs, its frequency. Well, based upon what we have here, how often did I get a 3.0? What's the frequency of getting a 3.0?
I'm gonna say 15.
So it is 15 because it occurred essentially 15 times
Because of the units, right?
because of the units, whereas the 3.5 occurred 12 times. And then don't forget what the final formula was. It wasn't just x1 f1 times x2 f2, but then it said, then divide this by the total number of data points, which in our case is 12, because we have 15 from the first semester and 12 from the second semester.
So 3.22.
So 3.2 bar, right? 3.22, which seems reasonable because it should be a little bit less than 3.25, which is the halfway point, but not really a lot less because 12 units and 15 units are pretty close to each other. So 3.22 is a more reasonable value. Does that make sense?
Yes.
And notice, by the way, it's exactly the same as finding the mean from a frequency table, right? The mean from a frequency table is the same thing. You multiply each data point times its frequency, add them together, and divide by how many data points you have, and that's the mean. So a GPA at the end of the day is just your average score, where each of your possible scores could have occurred a different number of times. So at the end of the day, and by the way, notice also, I can rewrite this as 3 times 15 over 27 plus 3.5 times 12 over 27, which is exactly the formula that we had in the previous page a little bit ago. Right here. For the mean is the sum of each data point times the likelihood that the data point occurs times its probability. 15 and 27 are not probabilities. Sorry, 15 and 12 are not probabilities, but 15 over 27 and 12 over 27 is the likelihood of each one occurring based upon my historical data. So that gives us 3.22, which hopefully makes sense. Are there any questions? I will entertain questions for a few minutes before we move on to chapter 13. So I'll give you 5, 4, 3, 2, and I understand now. Thank you. Wonderful. That is wonderful news to hear. Okay, so I'm going to stop sharing for just a minute as I load up the next chapter. Also, I got to remind myself, put up homework solutions. Put up homework for math to 11, and this will be chapters 10 and 11 because
Did we
I want-
actually do the quiz on 11 instead of 10?
ooh, now we have a fight.
No,
Okay.
it was me that said 10, but I'm changing my mind.
Okay. Well, that just sucks. Okay, so I will take a vote right now, 10 or 11. Wait. Let me first put in chat so I know when to do it from. I'm gonna say go, and then I want everyone, I'm gonna give you 5 seconds. That's it, 5 seconds. So have your answer. Wait for it. I'm gonna say go. I'm gonna type in go. And then after the word go, I want you to put your vote in. So I'm gonna go right now. Go. Oh wait, I hit the wrong person, but anyways, okay. So 11, 11, 11, 11, 11, 11, 11, 11, 11, 11, 11, 11, 11. Okay, it's a close vote.
Okay.
It's
It's close.
50-50, huh?
It's 50-50. Oh, and Alex wants that. Way to be that guy, Alex. Way to be that guy. So what was chapter 11? That's a great question. I don't know. I think it was the mean. I think 11 was the mean. So Alex said, I defy trends. Okay, so,
11 was measures of position.
okay, no, that was 10, I think. Maybe it was it, no, was that 10
No.
or 11?
That
I
was
don't
11.
know. Okay, the vote is for 11.
No, 10 was displaying quantitative data.
Oh, yeah, okay. Good, I prefer 11 anyways. Okay, so 11 it is. Alex, sucks to be you, but life will go on. I feel you'll pull through this. It might be tough for a little bit, but I have faith. I have faith in you. All right, chapter 13 on variability. Up until now, we have focused our attention on measures of position. Center. Where is the center? Where is the center? Mean, median, and so on. Now we are talking about variability. So, in fact, statistics has been called the study of variability in data. So variability is apparently a very important thing.
Wait, I'm so sorry. I have a question.
Okay.
For that formula, the x1 and the frequency over to n.
Yeah.
What if there's, because obviously we had a problem that had two data points only. If they have more, do you just do that over again as many times as
Yep.
what you have? Okay. So there could be like x3, x4, whatever.
It could be x3, f3, x4, f4, x5, x5. It can be anything.
Okay.
That's exactly it.
Thank
Okay.
you.
All right. So what do we have here? We have team 1, we have team 2. Team 1. Look at their heights. What do you notice about team 1?
Stable.
They're tall.
Stable. I like that word. Stable. Their heights are pretty uniform. What about team 2?
You to the left.
What do you mean to the left?
It goes like it's racing. It goes taller, like low, and then starts going higher.
Yeah, I mean, of course, these people could be standing in any order they want, so I wouldn't say that the point.
Okay, it's not a
to-
graph, so you're right.
Yeah, so I wouldn't say the point is that lower to higher, but what you see is for team 2 that their values vary more than they do for team 1.
There's various heights.
Yeah. Okay. Team 1 seems to be pretty much uniform, stable. I heard someone say consistent. Whereas in team 2, their heights, the ones in the middle are pretty stable, but you have that short one and the tall one that make the heights a little variable. Okay. And in fact, it says compare the means and variability of the heights of these two teams. If you actually do the math, 72, 73, 6, 76, 76, and 78, what do we get for the mean there? Anyone? What's the mean for both of them? Anyone?
75 for the first one.
75 for the first one. and
Oh, 75 for the second one.
75 for the second one. So they actually have the same mean. But this one varies a lot more about the mean than this one does. And we would like to have a measure, a quantitative value that we can assign to the data for how much it varies. So the California Common Core State Standards has this goal for 6th grade students. Students recognize that a measure of variability, for example, the IQR, the interquartile range, or the mean absolute deviation, the MAD, can also be useful for summarizing data because two very different data sets can have the same mean and median, yet be distinguished by their variability. So they recognize the mean and median alone is not enough. And for algebra 1, use statistics appropriate to the shape of the data distribution to compare center and spread of two or more different data sets. So whether it's Common Core, or whether it's for 6th grade, or whether it's algebra 1, we have to be able to measure variability and to compare variability for two different data sets. So in this section, we are going to learn about 3 different measures of variability: the IQR, the MAD, and the SD, the interquartile range, the mean absolute deviation, and the standard deviation. So facts: the mean absolute deviation is not used in practice. We don't use the mean absolute deviation. It's just never used. The interquartile range should be used whenever the median is your choice of center. And the standard deviation should be used whenever the mean is your choice of center. Why do we learn the MAD? Because it's a nice gentle lead-in to the standard deviation. So it's used in this section, used on homeworks, used for tests, but it's not used in practice. It's just a lot easier than the standard deviation mathematically. So let's get started. First of all, you'll notice that the one thing that is not used in these 3 is the range itself. The range is max minus min. So why not the max minus the min? What's wrong with max minus the min? So the answer is, 1, it doesn't really describe the data very well, because you'll notice in this diagram here, the mean in both cases is 18. I didn't do any math to do that. I spotted it immediately just by looking at the data sets. What giveaway is there in the data sets that makes the mean in both cases equal to 18?
It's in the middle.
It's not just in the middle, but it's symmetrically in the middle. So the data point on either side is perfectly balanced because you move out the same amount in either direction for A or for B, right? So it's kind of like, imagine you're like, maybe lifting weights or something like that, and you have the weights exactly the same distance. It's going to be in balance. So they have the same mean. They have the same range. But there's something about them. The first one, the data is all over the place. The second one, the data is all on the edges. So which one of those has the larger variability? So for this one, it's important to understand what the word variability means in the language of statistics. It's very easy to say, oh, this one does. Look, 6 different numbers. Whereas this only has 2 different numbers. Therefore, the first one varies more. That's not what variability is.
Professor, would it be the second one that has more variability?
Why though? So what definition do we want to use for variability that gives us an answer to the second one?
Would it be because they're all together, which I don't know how to put it in words. It makes sense in my head. I don't know how to explain it.
Gotcha. That happens to me all the time. But no, I think it's more like this. Variability is a measure of how far data points are from the mean. In the first one, the one on the left, 2 data points are close to the mean, 2 are medium distance from the mean, and then 2 are far from the mean, correct? Everyone with me?
Yep.
In the second one, everything is far from the mean. So on average, which one's data points are further from the mean? The first one or the second one? On average, which ones are further from the mean? The first one or the second one?
The
The
second.
second.
The second one, because they're all far versus some being far and some being close. So the one that has the larger variability is actually the second one, because variability is not how they vary, but rather how far they are from the mean. So why not the range? Because they have the same range, but the second one has a greater variability. Second reason, the range is very sensitive to outliers. You give one outlier and bam, the range shoots up. You get rid of that outlier, bam, the range shoots down. So the range is too sensitive to outliers. And the third reason is nobody uses it. It's just not used in practice. Of course, why is it not used in practice? Probably because of reasons 1 and 2. But nevertheless, it's just not used in practice. They might say the values range from 33 to 23, but no one says the range is 10. The range is just not used as a measure of variability. What is used is the IQR and the SD. So let's do the IQR first. We know from our study of box plots that we have a minimum, we have Q1, we have Q2, the median right there, we have Q3, and we have the maximum, correct? Yes?
Yes.
Okay, so the range is max minus min. That's the range. Uh-oh, not good for outliers. So what the IQR says is just give me this guy here, the middle 50%, Q3 minus Q1. I'm going to write it written above. The IQR is just straight up Q3 minus Q1. It's a number, like the range of the number, but rather than going max to min, we just do the middle 50%. The Q3 minus Q1, the middle 2 quartiles, the inner 2 quartiles, the interquartile range. And we use this. And again, we only use this with medians. We do not use it with means. I mean, you can calculate it for means if you really wanted to, but we don't normally do that. Does that make sense so far?
Yeah.
Okay.
Yeah.
Okay. Now, we have this chart here. That's not. Hey, there it is. Okay, so we have this chart here. It says the heights of children the same age are quite variable. We know this. Hopefully we know this, right? Not all 10-year-olds are exactly the same height. What is the approximate percentile for a 9-year-old girl who's 49 inches tall? So this is boys. Girls. Okay. 9-year-old girl. So let's find 9-year-old girl. That's age down here. So this is 9-year-old girl who is 49 inches tall. So here's the height, 49 inches. That is right here. Okay. So based upon this chart, what is the approximate percentile for a girl, 9 years old, 49 inches tall? What percentile is she in? Anyone? What percentile is she at? 9-year-old girl, 49 inches tall.
7.
Which one?
The 7th.
Okay, I can see that. Everyone else see that? 7th, 8th?
Ish.
Ish. Does everyone agree it's between the 5th and the 10th?
Yes.
Does anyone not agree? Or is not sure why? Okay, so, all right, we'll go with the 7th or 8th percentile. Is there more variability in the heights of 20-year-old girls or 20-year-old boys? Oh, wait, that's the next page. I missed one, sorry. How tall does a 12-year-old girl have to be so she is as tall or taller than 75% of the girls her age? How tall must a 12-year-old girl be to be as tall or taller than 75% of the girls her age? So 12-year-old girl, we'll go to that one. And we want her to be tall or taller than 25% of the girls. So where am I gonna, where should I put the sideways line?
Well, I thought you would put it at 75.
75 inches?
No,
At the
the
75th percentile, yeah.
So 75th percentile. So let's see where the 75th percentile crosses the
That should be at
12-year-old.
62,
60. Oh,
I think.
I was thinking 65.
Certainly
It's
see.
66, right? Like around, no, wait. Yeah, you guys are right.
Not
My bad.
56, right?
Yeah, no, I'm thinking over. Yeah. I'm
Yeah,
looking
if
where
you
it
saw
starts.
if you saw this 75th, then you might
Yeah,
say,
I'm
oh,
thinking where it
60.
starts. Yeah.
Right, but we want to follow this curve line down to 12-year-olds, and then it'll also be a little under 62 inches.
Mhm.
Does that make sense, Sabina?
Oh, sorry.
Because Sabina put in chat the wrong answer. Okay, good. Okay.
I'm
Huh?
still confused.
Well,
Wouldn't you have to be at least 66 inches tall?
why 66? Because you see 75th here by 66?
Yes.
No, but 75th, this is a 75th percentile curve. It changes based upon your age. You got to follow this curve around until you hit the 12-year-old mark.
Oh, yeah. That's right.
Okay, so for a 12-year-old,
I was just on the 12-year-old line and then 75. Oh, okay.
yes, that's what you're looking for. Makes sense?
Yeah. So, oh wait, can you leave it on the girls real quick?
Yeah, sorry.
I want to follow it. 75. Oh yeah. So it would be 62 at least 62 inches. So what would it be like at least 62 inches, or would it be 63 and above?
No. So you would say that for a 12-year-old girl to be taller than 75% of the girls her age, she would have to be roughly 61.5 inches tall.
Okay.
Okay. Next, how tall must a 12-year-old boy be to be in the top 75%? So how tall must a 12-year-old boy be to be in the top 75%? So 12-year-old boy. '75 percentile. A little shorter. Do we agree?
Yeah.
Everyone agree?
Yeah.
3.5.
Okay. Now, how can you tell from the chart when children are growing the fastest? When are children growing the fastest?
Where the line is steeper.
When the line is steeper. Excellent.
So that would be closer to the beginning.
Well, I mean, let's take a look. In the beginning, whoops, I hit the wrong button. So draw, okay. So if you look in the beginning, let's follow this percentile. If you go in this beginning, that seems to be the steepness at the beginning. And here, it seems to be less steep. Here, it's pretty steep again. You see how these curves are kind of like in the direction of growth at different times. So yeah, I mean, I would say pretty steep here, but also pretty steep over here in this area, which is right around 13, 14 years old. Do we see that?
Yep.
Everyone see what I'm talking about? How about girls? Where do girls grow the fastest, give or take? I mean, obviously babies grow very fast, but after that, where do girls have their growth spurt usually?
Around 12.
And
Yeah, around 11 or 12, give or take. It seems the girls grow at 11 or 12 inches a year. So girls, have their growth spurt a little younger, but they tail off at a lower height as a general rule than boys who have their growth spurt later, but tail off at taller. I did not what? I'm sorry, Genesis. I forgot what I asked.
Growth
Oh no. Huh?
My growth spurt was like maybe around 13, 14.
Oh, I'm sorry. Sorry, I thought maybe I asked something and I didn't know what was happening. Yeah, this is statistics, right? So there's always going to be variability, right? Not everyone does. I just read this article yesterday. Apparently the tallest woman in the world is some Turkish woman. She's like 7 feet something tall. So there's always the exceptions to the rule. So just remember, you guys are exceptional if you do not have your growth spurt at the same time as everyone else. So Genesis, you are exceptional. Just remember that. All right. Let's take a look. Is there more variability in the heights of 2-year-old girls or 14-year-old girls? And why?
it'd be 2-year-old girls, right?
No.
Wait, you're on boys.
Well, it's probably the same on girls or boys, but if you look at girls, 2-year-old girls,
Oh, because they're all around the
They're-
same.
yeah, there's like a 5-inch difference there, 6-inch difference there.
And 14 is a lot. Is
Right.
way. Yeah,
By
yeah.
the time they hit 14, which is this one here. Oops. I think it was this one. So you can see that there's a much bigger, right? 2, 4, 6, 8, 10 inches. Almost twice as much variability. Right? Makes sense?
Yes.
Okay. Now, better question. What is the 25th percentile, the 50th percentile, and the 75th percentile for 4-year-old boys? And therefore, let's compute the IQR. So 4-year-old boys. So the first thing I want to do is draw a straight line as best I can on 4-year-old boys. And then which is the 25th percentile? It's curve number 3. So this is curve 3. And then the 75th percent, the 50th percentile is the black, is the big bold curve, which is about there. Oops, that wasn't straight. So the big bold curve is about there. And the 75th percentile is the third curve for the top. It's about there. Okay, so what is the 25th percentile for 4-year-old boys?
39.
39. What is the 50th percentile for 4-year-old boys?
I put 40.25.
Okay. All right, I'll just put about 40. It's maybe 40.1, 40.2. And what's the 75th percentile?
41.
About 41.5, I would say. Because remember, each solid line is, this is a whole number,
Right.
okay? So what is the IQR?
Oh yeah, it's a little below.
What's the IQR? Anyone? What's the IQR?
Uh,
Are we doing 41.5 minus 39?
Yes, we are. And what do we get?
2.5.
2.5 inches. The IQR is 2.5 inches. IQR is nothing more than Q3 minus Q1. Yes?
Yep.
So which one would be the Q1?
Q1 is the 25th percentile, which would be the smaller number. Q3 is the 75th percentile, which is the bigger number,
Got it.
right? Because 25% of boys aged 4 years old are 39 inches or less. 50% are 40 inches or less. 75% are 41.5 inches or less. 100%, well, there could be a really tall boy out there, a big outlier, which is why we don't go all the way to 100%, because the typical boys are between the 25th percentile and the 50th percentile. Okay. So the IQR in the box plot. I believe we already had this example in a different context. I think we did. Remember the name game problem? We did this one once, I believe. Everyone, did we do it? Anyone home?
Yes.
Everyone? I think so, right? So which of these three has the greatest variability? Group 1, group 2, or group 3? Which one has the greatest variability?
Group 2.
Group 2. Not only is it the greatest range, if we ignore the outlier in group 1, but it has the greatest IQR. In fact, what is the IQR of group 2? What is the IQR of group 2?
Maybe like
About-
35. If we're gonna put the first line at 5.
Yeah, I mean, this is 5 here, 40 here, about 35. Somebody else was speaking up. Were you agreeing, or did you have a different answer?
Yes, I was going to say the same thing.
Yeah, about 35. So the inner 50% of people would have a 35% variability between the best and the worst in this regard. If we ignore the bottom 25% and the upper 25%, which is what the IQR does, it just ignores them. All it cares about is the innermost 50%.
How did you get the 35? You just went in the middle?
Well, no, I went to Q3, which is right here, about 40,
Mm-hmm.
and Q1, which is right there, about 5, and subtracted them.
Okay.
Oh, so the median doesn't really.
Median's irrelevant for the IQR.
Oh, what the hell? Okay.
They're
thank-
completely and utterly irrelevant. I mean, obviously, you need the median to calculate Q1 and Q3. If you recall, first you
Right.
find the median, and then the median of each side, that's Q3 and Q1. But once you have it, you don't need the median anymore. Okay? Yes?
Yeah.
Okay. Now we get to what's called the MAD, the mean absolute deviation. And Chet, you have nothing to be sorry for. Oh, thank you. Oh, that's so sweet of you. Oh, I love little compliments like that, really make my day. So the mean absolute deviation. One way to think about the variability in data is to examine how far the data values are from their mean. For example, 4 Girl Scout troops. Each one had 9 boxes sold, and these are the numbers for troop A, for troop B, for troop C, and for troop D. And oh, smiling at me, thank you. Anyways, if we make a dot plot for all of them, here's A, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1 each. B was 3 2s, 2 6s, and 8, 2 9s, and a 10. 3 2s, 2 6s, and 8, 2 9. Okay, good. So here are the dot plots for all 4 troopers or troops. What do you notice just by looking, by the way? What's the mean of A?
6.
6. What's the mean of C?
6.
6. What's the mean of D?
6.
6. All of those are perfectly symmetric about the center, so they perfectly balance in the middle. B is not as easily determined, but we can do it by seeing how many steps it takes to bring everything to 6. We'll see if it's also 6. This one, 1, 2, 3, 4 over, and there's 3 of them, so a total of 12 this way. This one takes 2. This one takes 3, but there's 2 of them for a total of 6. And this one, 1, 2, 3, 4 takes 4 for a total of 12. And so 12 on the left, 12 on the right. The median is also going to be 6. They all have the same mean, which is great. The question is, do they all have the same variability? So we're not going to do it by the IQR method. We're going to do it by a different method. And here's what we're going to do. Let's look at Trooper A for a second. How far is 2, this one here, this data point, how far is it from the mean?
Four,
And how about this one?
3,
This one?
2, 1.
This one?
Well, isn't that the mean?
So how far is it from the mean?
Oh, 0.
This one?
1, 2, 3, 4.
So what we're going to do is we're going to take all those numbers, how far each one is from the mean, and add them all together. And we get a total of 20. If we do the same thing for C, how far is this from the mean?
4,
How about this one here? How far is it from the mean?
4,
How about all of these? How far they are from the mean?
0.
0. So if I were to write all the possibilities for troop C, it will be, I have 1 at 2, which is 4 from the mean. I have a lot of them at 6. 4, 5, 6, 7 at 6, which are all 0 from the mean. And then I had the last one at 10, which is how far from the mean? 4. What's the total there?
8.
8. So which one on average has more away from the mean, A or C?
A.
A. So troop A is more variable than troop C, because on average, the data points are further from the mean. Do we agree?
Yeah.
Okay. This sounds like a wonderful and easy method of determining which one has a greater variability. It's really, really straightforward, right? You just see how far each one is from the mean, add them up together. Whichever one has a bigger number, that must be the one that is more variable. Yes?
Yeah.
Seems nice, right? Well, we got a small wrench in our plans because now a new troop came out. Troop E had a lot of participation, had 40 girls. 20 of them sold 5 boxes and 20 of them sold 7 boxes. What's the mean for troop E? Again, think balance. What's the mean for
Yeah,
troop
it'd be
E?
6 as well, right?
It's gonna be 6 as well. So what is, if I look at each data point and how far it is from the mean and I add them all together, what would I get? How far is this one from the mean?
1,
And this one?
1, 1, 1, 1, 1.
They're all ones. So what's the, if I add them up together, what do I get?
Is it 40?
It's 40 because there's 40 data points, right?
Yeah.
Now we got 20 for A, and now we're getting 40 for B. By looking at these data points, would you say A on the average is further from the mean than B, than E?
Well, no, it would be
I mean, forget the numbers. Just look at A and look at E. Which one seems
No, because they're exact replicas. I mean, they look exactly the same.
A and E? Here's A. And here's E.
Oh, I'm sorry. I'm looking at them as if they were side by side, you know? Like
Oh,
if
no,
how
no,
you
no, no.
did the other
So,
one.
yeah, so A is remember what A was? It was 2, 3, 4, 5, 6, 7, 8, 9,
Yeah,
10,
yeah.
21. So which of these seems to be more spread out from the mean, A or E?
E.
E does not look more spread out. Look how close everything is from the mean here.
A because
They're
everything
all
has
one
space in
away.
it.
Huh?
Doesn't A because it has spaces?
Well, look how far away some of these guys
Yeah,
are from the
that's
mean.
Yeah, there's spaces in between everything.
But E, everything is pretty close. Tell you what, it's 3:15. I don't want to keep you. We'll start right here at this one next time. Okay, well,
Wouldn't it be because there's so many dots?
so that's the reason why. We'll need to take that into account. We'll need to take that into account. Okay,
Have a good
everyone.
weekend. Be
Have a
safe.
great weekend. I remember I'll put the quiz up. I'll put the homework solutions up. So do it and stuff. Okay, quiz will be for next Thursday. I'll give you a week. Okay, Alex. Jeez.
Thank you.
Oh, okay, that's good. Okay. You're putting it up, but it's not due till next Thursday?
Can't get anything
Yeah,
by
because
you.
of midterms.
Perfect, good. Yeah, I mean, I started midterms too.
I understand.
Thank you.
Okay, I'm gonna pause right